Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to show you how to write the molecular complete ionic equation and net ionic equation for a chemical reaction. In this video I'm going to go over silver carbonate solid that reacts with acetic acid to produce a clear bubbly solution. So let's get into this. They're giving us the names of the substances. So you need to know how to go from the name of your substance to the formula. If you need help with that, I have videos for that. I'll put those in the description below. What we're going to do here is we're going to take this. We can recognize this as a ionic substance because here it's a metal and non-metal, so silver carbonate. And so what we need to know about the names of the ionic substances are that the two names of the ions come together to form the name of the ionic substance. So we just need to work backwards. So we're given two parts of the name. Each part represents the name of the ion. So we have silver ion and we have the carbonate ion. So all we need to do is write down the formula and the charges. So here silver is Ag, and silver is a transition element. So we would normally think that we would need a Roman numeral to identify the charge, but there's no Roman numeral here. So how do we know the charge? And so this is one of those exceptions to the rule. So silver doesn't normally have variable charges. In very specific circumstances, it could have a different charge, but for the most part, it's always ever going to have a +1 charge. And that's just something you need to memorize. And there are other exceptions like cadmium only has a 2+ charge, zinc only has a 2+ charge. And there's also exceptions with the main group elements too, right? So main group elements, you might think only ever have one charge, but then there's lead. Lead is technically in the main group elements, but it could have multiple charges. Tin is also an example. So there are exceptions you have to keep in mind, and silver is one of those. So silver has a +1 charge, and then carbonate is a polyatomic ion. You just need to know what the polyatomic ions are and their charges. Your teacher probably gave you some sort of handout or sheet of paper that has the common polyatomic ions on it. You probably need to memorize those. I have a video or a couple of videos on memorizing the polyatomic ions. I'll link those in the description as well. So carbonate is going to be CO3 2- charge. So now that we have the ions, all we need to do is put them together in a formula. And when you do that, you got to balance the charges. So you need to make sure that the total negative and positive charges are equal. And so here we have a +1, here we have a -2. So we're going to need two silver ions to balance the charge of our carbonate. That's one way to do it. Another way, you could just do the crisscross method, right? So the crisscross method, you take the number of the charge on this ion, you write it as a subscript for the other ion. So here this is a 1, so we would write a 1 subscript there. We don't write ones, so we would just write Ag2 subscript with CO3. So you'll notice I don't have any parentheses here. You only use parentheses for polyatomic ions when you have more than one. So we only have one polyatomic ion here, so we're good. So this is our formula for the first substance, silver carbonate. What about acetic acid? Well, acetic acid here, you have to recognize that this, of course, is an acid. There's two ways of naming acids. If you're not familiar with naming acids or you need a refresher, again, I have videos linked in the description. But here, you'll notice right away that this has to be an oxyacid. There's two groups. There's your oxyacids and your binary acids. And so the binary acid is where you don't have oxygen involved. It's just two elements. One of those elements is hydrogen, and then you have another element. So those are your binary acids. So for your oxyacid, you have an acid with hydrogen, but then that hydrogen is bonded with some sort of polyatomic ion that has oxygen in it. So your sulfate ion, your sulfite ion, your nitrate, nitrates. your phosphates, phosphites. And so acetate, acetate ion, it has oxygen in it. And so that has hydrogen bonded to your acetate ion, creating the acid. So here we have acetic acid. Again, one of the dead giveaways for a binary acid is that it begins with hydro, and you don't see hydro here. So it's definitely not a binary acid. It's going to be an oxy acid. So you need to know what the acetate ion is. So the acetate ion is C2H3O2 minus. And so to get acetate from that, or acetic acid from that, you're going to add H plus to this. You're going to add hydrogen to it until the negative charge is balanced. So we have a -1 here. Hydrogen is an H plus, so that's 1. So all we need is 1 hydrogen to balance this. So the formula for our acetic acid is going to be H. We write the H first for acids, and then we write the ion, C2H3O2. And so that's it. So now that we have our two reactants, now we need to predict our products. And the way you're going to do that is, one, we're going to notice here that we have an ionic substance, and here we don't have an ionic substance here, but we do have an acid, and acids are not ionic, but they can ionize into ions. And so we can treat this like an ionic substance. And what do you do when you have two reactants that can break down into ions? This would indicate that you have a double displacement reaction. So how do you figure out the products for a double displacement reaction? Easy. You just take the inside ions, put those together, and then the outside ions are going to go together. And then you form the formulas for those. So remember, you need to balance the charge. So here I have silver. Silver has a +1 charge. And then I'm going to put that with acetate. That has a -1. So they both have the same charge. So I only need 1 each. So that's going to be Ag and then C2H3O2. So that's my first possible product. And then here I'm going to have the hydrogen going with the carbonate. Carbonate has a 2- charge, and hydrogen has a plus charge. So I'm going to need 2 hydrogens to balance that charge. So here it's going to be H2. So I need 2 hydrogens and then CO3. So now that I have my products and reactants, I need to balance the equation, and I need to figure out what the states of matter are. So here I have silver carbonate. We're going to need, in order to figure out whether this is solid or aqueous, we need our solubility rules. You probably have one from your teacher, or you could easily find one on the internet. So according to solubility rules, it says carbonates are insoluble except what? When you have a group 1 metal, or that would be your alkali metals, or ammonia. And here we have silver, so that is not one of those. However, we're told that it is a solid in this case, so we'll write solid. Okay, so now what about your acetic acid? This is where you need to identify whether this is a weak or strong acid. So you need to know what the strong acids are, and there's 6 of them, sometimes 7, depending on where you look. But they're mainly 6 6 strong acids. That would be like hydrochloric acid, hydrobromic acid, sulfuric acid, and so on. Acetic acid is not a strong acid, it's a weak acid. And why is this important here? It's important because this does not come apart. So weak acids and weak bases, what defines them as weak is the fact that they hardly ever ionize into ions. They will stay together. The hydrogen will stay bonded with the other part of the molecule. So your acetic hydrogens do not come off very easily. They'll stay together. So this molecule, for the most part, by and large, stays like this. It doesn't come apart. But it will dissolve in water, so it's aqueous. Why do I bring that up? Is because that's going to be important when we write our ionic equations, our complete ionic and our net ionic equations. All right, what about acetates? Acetates are soluble according to our solubility rules. Acetates are all soluble. Anytime you have an acetate, it's going to be soluble. So this is aqueous. And again, you can identify this here. You could say, oh, this is an acid because it's got H2, and you would be right. This is, again, another weak acid. So again, this isn't really going to fall apart. It's not going to ionize very easily. But there is one thing you need to keep in mind here. So again, whenever you have carbonates, you should be keeping in mind gas evolution reactions. So anytime you have a carbonate and you're reacting it with an acid and you get the carbonic acid. Carbonic acid and other carbonates can easily break down and decompose into carbon dioxide and something else. But here, this will decompose into carbon dioxide and water. So this is what causes your bubbly solution. This is why you're getting bubbles, is because this is breaking down into CO2 gas and H2O liquid. So that is part of the reaction there. So now that we have that settled, let's figure out the rest of this. So we have our solid, we have aqueous. So we have all of our states. We have a balanced equation. So we're done with the balanced molecular equation. Next thing is our ionic equations. We're going to do the complete ionic equation first. So with the complete ionic equation, you are going to separate everything into its ions. And that means anything that is aqueous, any ionic compound that's aqueous, we are going to separate those into its ions. If we have a strong acid or a strong base, we're going to separate those into ions as well. Anything that's a liquid, solid, or gas, we keep together. Anything that is a weak acid or a weak base, we're going to keep those together because, again, like I said, those do not ionize or break apart into ions very much at all. So we're going to keep those together. So let's go ahead and do that. So here we have a solid, so we're going to keep that together. So Ag2CO3 solid. And this is a weak acid, so we're going to keep that together. So that's HC2H3O2 aqueous. And we're going to go to our products. Here we have aqueous. This is going to come apart. We have an ionic substance. It's aqueous. So we're going to separate the ions. So we have Ag plus aqueous. And you'll notice that when I separate the ions into their individual, separate the ions from their formula here, I'm going to write the charge. So here, when they're in the formula, you don't write the charge. And then here, you do write the charge when you separate them. And so that means I'm going to have a C2H3O2 minus aqueous. And then I have water and carbon dioxide that I'm going to keep together. So H2O liquid plus CO2 gas. And so that, ladies and gentlemen, is your complete ionic equation. So now all we have left is your net ionic equation. And so when we do the net ionic equation, all we're going to do is we're going to remove from the complete ionic equation all the things that are called spectator ions. And how do we identify the spectator ions? There's a couple of ways. First, you might look at the products that are formed. We have water, carbon dioxide, and so we might look at those and say, okay, what ions here, what was involved in that reaction, what formed those? And then we would keep those because they're part of the reaction. Anything that's not involved in forming those products, we would eliminate. Another way you could do it is by looking at both sides of the equation, looking at the reactant side, looking at the product side, and seeing what stays the same, what does not change at all. So you could look at your silver and your carbonate, they're in a solid together, but notice that now the silver is aqueous and the carbonate is in your water and your your carbon dioxide. So that changed. So that's going to stay. And here we have our hydrogen. So the hydrogen is also part of the water and the carbon dioxide, mainly the water, because that's where the hydrogens are. So the hydrogen there is part of the reaction, so that stays. And then here we have the acetate ion. Notice that the acetate ion is part of the compound acetic acid. It is not by itself, but here it's by itself. So that changes as well. So all of this is part of the reaction. So here, there are no, how do you say, there's no spectator ions. So here your complete ionic equation, CIE, is the same as your net ionic equation. So your net ionic equation is the same as the complete ionic equation. So there are no spectator ions. So I hope this is helpful. If you like this video, if you learned something from this video, let me know in the comment section what you think, and let me know if you have any questions. Hit the like button and subscribe to the channel. Hit the notification bell. Thanks for joining me, and have a great day.